Hello and welcome. Today we're going to dig into a concept from physics you probably learned about in high school and maybe haven't thought about since, heat capacity. But as you're about to see, its true meaning is way deeper and honestly way more fascinating than you might remember.
So let's just start with the big question. What is heat capacity? I mean, it seems simple enough, but trust me, there's a real puzzle hiding in that old textbook definition.
We all learn this, right? It's just the amount of energy you need to pump into something to make it 1 degree hotter. You know, a swimming pool has a higher heat capacity than a puddle. Seems totally straightforward. But this simple definition completely falls apart when things get really interesting.
Okay, think about a glass of water as it turns to ice. You are constantly pulling energy out of it, right? But for a while, its temperature just stays locked at 0 degrees Celsius. The temperature changes 0, but the energy change is not. So, if you plug that into the simple formula, energy change divided by temperature change, you get a heat capacity of infinity. How can a real physical property be infinite? This isn't just some math quirk. It's a huge clue that our basic definition is missing something really important.
So to solve this mystery, we kind of have to throw out our old way of thinking and adopt a whole new language. A language that comes not from classical mechanics, but from information theory. We have to start using the language of uncertainty.
The first new word in our vocabulary is multiplicity. And think of it like this. If you have a certain amount of thermal energy in an object, multiplicity is the total number of different ways you can distribute that energy among all its atoms and molecules. It's just a count of all the possible microscopic arrangements for a given total energy.
And this leads us straight to entropy. Now, you've probably heard it called disorder, but that's a bit misleading. A much more powerful way to think about it is as a measure of our uncertainty. See, if a system has a high multiplicity, tons and tons of possible arrangements, we have a really high uncertainty about which specific one it's in at any given moment. So entropy, in this view, is just a measure of that missing information.
And look, this isn't just some convenient analogy. The physicist E.T. Jaynes made it completely explicit. Physical entropy is statistical uncertainty, and its most natural units aren't joules per Kelvin, but units of information, like bits. This single insight is the key that's going to unlock everything for us.
So, if entropy is all about information, what does that make temperature? Well, it means we can now redefine temperature itself in this powerful new language.
This new perspective completely flips how we think about temperature. The old view says it's all about how fast molecules are jiggling, but the new information-based view is so much more profound. Temperature is the energy cost to increase your uncertainty about the system by 1 single bit. Hotter things, well, they require less energy for each new bit of uncertainty.
Now, to capture this idea with math, physicists use a dimensionless quantity, the total thermal energy E divided by K, Boltzmann's constant, times the temperature T. You'll see it written as E over KT. This ratio, it turns out, is incredibly meaningful.
And here's why this ratio is so crucial. E over KT tells us exactly how the system's uncertainty grows as you add energy. It's what's called the multiplicity exponent. It literally tells you how many new bits of uncertainty you gain every single time you double the thermal energy in the system.
But this elegant new quantity has a fatal flaw for actually using it. Its value is completely dependent on where you decide to set the 0 point for energy. If you change your baseline, the value of E over KT changes, which, isn't very helpful for an objective physical measurement. We need something better.
And this brings us right back to the hero of our story, heat capacity. It turns out, the very thing that seems so puzzling at the start, that infinite value, is actually the key to solving this whole problem.
The natural dimensionless unit for heat capacity is CV, that's the heat capacity at constant volume, divided by Boltzmann's constant, K. Just like E over KT, this is a pure number. No units of joules or Kelvin, just information.
And this is what makes heat capacity so powerful. Think of it less like a snapshot and more like a speedometer for energy. It doesn't care about the absolute amount of energy in the system, only the rate of change in how that energy can be stored as you add more. That's why it's a local probe, and it's totally independent of any arbitrary 0 point. It's the objective tool we were looking for all along. Okay, so we have our tools. We've reframed temperature, and we've found our perfect probe in heat capacity. Let's go back to our original mystery and see physics in a whole new light. Let's go back to that freezing water. What happens if we try to analyze it not with the old, broken definitions, but with our two new information-based quantities?
Well, if we plot our first quantity, E over kT, for water as it goes from ice to liquid to steam, we get this. It's just a mess. Because its value depends on that arbitrary energy zero we talked about, there are no clear stable regions. It's pretty much impossible to tell what's going on just by looking at this chart.
But now, look what happens when we plot our new hero, the dimensionless heat capacity, CV over K. Bam! The story becomes crystal clear. Those infinite values we were so confused about, they're now these sharp, finite peaks. They are giant signposts screaming at us that right here, at this exact point, the entire method of storing energy in the system is fundamentally changing. The number of ways energy can be arranged, the multiplicity, is going through a revolution.
And this information-centric view is just unbelievably powerful. It doesn't just solve the water puzzle, it elegantly explains why, at very low temperatures, certain ways of storing energy in a solid just freeze out and become totally inaccessible. It even explains bizarre concepts like paramagnets reaching negative absolute temperatures, a state that's actually hotter than infinity, where adding energy decreases the system's entropy. Wild, right?
So what's the ultimate takeaway here? Heat capacity is not just some boring number from a textbook. It is a direct, physical measure of how the information capacity of a system changes with temperature. Those peaks at phase transitions are just explosions of new informational possibilities.
And that leaves us with a final, really tantalizing thought. If a fundamental concept we all learn in school is actually, secretly, about bits and uncertainty, what else is? What other physical laws are just waiting for us to see them not as laws of matter and energy, but as the laws of information itself?